Thank you, Laura, Maria, Liam, and Oliver, for setting all this up and inviting me to speak. What I'd like to tell you about is a generalization of the Shuffle Theorem, in which the combinatorial side involves lattice paths under any line. And I will probably spend most of the talk just telling you reminding you what the original Shuffle Theorem says, and what our generalization is, and then give you some hints about the proof, because we have a new technique which makes things simpler than other proofs. This is joint work with Jonah Blasiak, Jennifer Morse, Anna Punn, and George Seelander. So here's the classical Shuffle Theorem. I've written it as an identity there in green. And this was conjectured by Hagelin, Lohr, Remmel, Ulyanov, and myself, and proved more than 10 years later by Carlson and Mellett. And I'd like to go over what the various ingredients of that identity you see there are. The left-hand side is algebraic and representation theoretic. The right-hand side is combinatorial, and we'll talk a little bit about both. So let's start with the left-hand side. So EK is the kth elementary symmetric function, and nabla there is an operator which acts on symmetric functions. And it's defined in terms of Macdonald polynomials. I'm not going to give you the precise definition, but the Macdonald polynomials are its eigenfunctions, and the eigenvalue is a monomial in T and Q. And this operator is, along with some others, is an important piece of the theory of Macdonald polynomials. And one reason why this is particularly interesting is that when you apply it to the kth elementary symmetric function, so you get what we have on the left-hand side, this symmetric function, which depends on Q and T because nabla does, if you expand it in Schur functions and look at the powers of Q and T in it, then in the usual sort of correspondence between Schur functions and irreducible characters of the symmetric group, it gives you, and the Q and T powers tell you the grading, it gives you the double grading, the character as a doubly graded space of the ring of diagonal coinvariance for the symmetric group SK, where you would let it act on a polynomial ring in two sets of K variables diagonally, meaning both variables simultaneously, and then look at the coinvariance means you mod out by the invariant functions without constant term. Look at the quotient ring. And so it was noticed years and years ago, way back in 1994, when Garcia and I were working on this, that diagonal coinvariant ring at that time conjecturally appeared to have some kind of remarkable links to combinatorics, with Dick paths and parking functions and other things appearing in its character. Now, the fact that nabla of EK is a formula for that character comes from geometry and representation theory using Hilbert schemes and so on. But what links it to the combinatorics is the identity which we have at the top of the page, which is the Shuffle Theorem. At that time, it was the Shuffle conjecture. And the right-hand side is the combinatorial side. So I also want to explain what's on that side. So I've written it again at the top of the slide just so you can see it. So first of all, let's look at what the sum is over. So these lambdas are going to be Dick paths, lattice paths under the line from the points at K on the X and Y axes. And there I've drawn one in green. And then there's some data associated to this lattice path that make up all the ingredients of the other stuff in the sum. So one of those is the area. This is the simplest statistic. The area between the lattice path lambda and the highest such path, which in this case is a staircase that would fit under the line. And so in this picture here, I've shaded all the boxes in between lambda and the highest path in orange, and if you count them, you can see that there are 18 in this example. So that's the area, and that gives you the T power on the combinatorial right-hand side of this expression. Then we come to the Q power, and that involves a statistic called the D inversions. But what it really is, it's the number of hooks in the Young diagram that's bounded by lambda, which are balanced in a suitable sense. So what we do is we look at the region that's in between, sort of in here, in between lambda and the axes, and that we think of that as a Young diagram. And then we look at the hooks of various boxes, and we say that a hook is balanced if its arm, which is the horizontal part of the hook like that, is equal to the leg. Or, so this yellow hook is balanced in that way, or if the arm is one more than the leg, like this in this orange hook, where the arm is one more than the leg. So those are the balanced hooks, and we count them, and that's this DIN statistic. And for some reason, which will become apparent later, I just want to point out that you can write the condition that the arm is equal to the leg or the leg plus 1 as this inequality that the leg over the arm plus 1, the interval from the leg over the arm plus 1 to the leg plus 1 over the arm contains 1 minus epsilon. The epsilon's in there because if the arm was equal to the leg plus 1, that right-hand thing would be equal to 1, but I want to avoid any ambiguities about what to do when inequalities are equalities. Okay, so that's the DIN. And then the last bit in the sum is an LLT polynomial. So here I have to explain in particular what that index nu of lambda is. In general, an LLT polynomial, and I'll describe what those are on the next slide, but in general, they're indexed by some tuple of skew Young diagrams. These ones are relatively simple because every skew shape in that tuple will be a single row skew shape. So it's an LLT polynomial indexed by a tuple of single row skew shapes. And you construct them from the lattice path lambda by, for every run of south steps in lambda, you set up a row of a corresponding length. So what I've done here is I've taken the first here, south run in lambda has 3 steps, and there's a corresponding row in my tuple of 3 boxes. And then there's an empty south run, which I've of 0 at the next one. The next non-empty one is 2 steps, and there's a row of 2 boxes in my tuple. But the ordering in which I put those, and also the offsets of them from where the boxes start, that depends on lambda. And so if you look carefully, you'll notice that I've actually changed the picture a little bit from the previous slide, and that boundary line is not, I've moved the lower endpoint of the boundary line here over to the right a little bit so that its slope is no longer 1, but 1 minus epsilon. And so what you do is you look at the distance from below the boundary line to where those various south steps are. And that distance tells you how to offset the boxes. So for instance, this row of 2, this south run of 2 started 1 step below the boundary line. And because of that, I put the boxes starting, starting offset by 1 box, whereas the first one started on the boundary line. So that first one there is not offset. But I've also, the order in which I would put them is such that the offset plus sort of epsilon times the index is in the same order as the distance between that slightly tilted boundary line. Now, what happens here, because the endpoints of the boundary line are the same and the original slope was 1, is that when I tilt it, I make that little extra epsilon factor increase from left to right. So these rows end up being put in the same order as the actual south steps that you see on the path. But with lines of other slopes, that would not happen. They would be shuffled into some different order. All right, so that's the recipe for constructing a set of rows attached to a lattice path from the lattice path and its position under this bounding line. Now, let me define what an LLT polynomial is generally. It's a symmetric function. It's given by a formula much like a Schur function that you just are going to look at all semi-standard Young tableau on your tuple of shapes. Take a monomial x to the t, which is the usual weight of a tableau. But now we also weight it with a q power, q to the I of t. where I is the number of attacking inversions in the tableau. And so those are inversions between entries of the tableau when you read them in a certain order and between certain boxes in certain positions. And so the way this works is the reading order is you just go column by column. So you read this one and then that one and then this one and then that one and so on. And in that order, if you see two numbers in the tableau that are out of order, like this 4 followed by the 2, which are in the same column as the 4 and the 2 are, or which are in a column and then in a lower row in the next column, so like the 7 and the 1. Okay, so the total of the position of the box j plus epsilon times the index is supposed to, that's the reading order. You go in increasing order of that, and if the two boxes you see are in increasing order of that, but the difference in that is no more than 1, then that counts as an attacking pair. And if you see an inversion in there, then that's an attacking inversion. You count those up. So it's an elementary, although not obvious, fact that these are in fact symmetric functions. More subtle is that they're in fact Schur positive, and really the only good proof of that we have uses Kajian-Lustig theory. But as a monomial expansion, they're completely combinatorial. Here's an example, just so you can get a feel for what these kind of things look like. So on the left half of the slide, you see nabla of E3, the k equals 3 case of this. And what I've done is I've arrayed the q and t powers into kind of an array. So something like this red Schur function here, what that means is that there's a term which is that Schur function times q to the 1 times t squared, because it's in the q to the 1 t squared box, and then you would add all this up. And so you remember I said at the beginning that this nabla of E3 gives the character of the ring of covariance for the symmetric group, in this case S3, as a doubly graded module. And so this is a picture essentially of that, saying in degree 0 you have the trivial character, which of course is corresponding to the fact that you have just the constants 1 in that degree. But then in like degree 2 in the x variables and 1 in the y variables, you have the sign character by this this one here that I just circled. And I've colored them so that you can see on the combinatorial side, when you add up that sum, which comes from what. So the orange lattice path here, when you work out the t to the area, q to the din, for that one it's q cubed. Then you multiply it by this LLT polynomial in q inverse. So it'll go from q cubed, the q cubed box, off to the left with decreasing powers of q. And I've indicated the terms that it contributed in the same color, orange. And then the yellow one contributes these yellow terms here, and so on. Okay, so the left-hand side has an algebraic definition, but the right-hand side kind of gives a combinatorial recipe for it. Well, there's an extension of this where the line is more general than just from K to K. And this was conjectured by Francois Bergeron and Garcia and Sergolevin and Shin. And it's also been proved by Mellett. And what we do is we now consider a line connecting any integer points on the two axes. We write those integer points in the form Km and Kn, where K is their GCD and M and N are coprime. And then we will have, again, an identity that looks somewhat like the one before, with a couple of small changes. The right-hand side is a similar sort of thing. It's a sum over paths under the line. You have the area. You have the dinv, but the dinv now depends on a number which is essentially the slope of the line, which would be n over m here. But we're going to subtract epsilon again because it's going to involve comparisons with rational numbers, and we want to remove ambiguities. And then an LLT polynomial constructed exactly as I told you before, but now relative from the path relative to this other line. And the left-hand side is also something a little bit different, and that we have to talk about. So on the left-hand side, what we have is a certain operator on symmetric functions. which I'm denoting ek of minus x mn. This is just the notation I like for it. It's an operator that lives in the Schiffman algebra, which turns out to be the algebra that all the operators that had arisen in the theory of Macdonald polynomials, when you sort of package them together, they form a beautiful algebra, which is the elliptic Hall algebra of Berman and Schiffman. And the fact that they do this was discovered a number of years ago by Feigen and Symboliak and Schiffman and Vassereau sort of independently. So you apply this operator to 1, and you get a symmetric function on the left-hand side. And it so happens that when n equals 1 in this thing, then you get the nth power of nabla applied to ek, right? So the actual original classical shuffle conjecture paper also had the conjecture for nabla m of ek, but then this kn version is more general, which is where the n can be arbitrary. But the left-hand side reduces to the old classical one when n is 1. And the DINF has also changed a little bit. It's now the number of hooks that are balanced relative to the slope p of the line, which is, or the slightly adjusted slope, n over m minus epsilon. And again, we could define it by the same algebraic, kind of formula that p is between the leg over arm plus 1 and the leg plus 1 over the arm. But geometrically, what that means is that a line of that slope passes through the upper end and the right-hand end of the hook. All right, so you count the hooks that are balanced in that sense, and that gives you the Q power. And then you take your LLT polynomial as before and put that all together. And that is the combinatorial expression for this Schiffman algebra operator applied to 1. So let me tell you what our theorem is. Now we take any positive real numbers r and s, and we look at the point with coordinate s on the y-axis and the point with coordinate r on the x-axis, and we connect them by a line with the slope p equals s over r, which you can always tilt the line a little bit without changing the lattice paths under it. So we'll always do that and assume p is irrational, so we never have ambiguities when we compare it with a rational number. And then we'll have a formula where the right-hand side is the same kind of thing you've seen before. You have t to the area, q to the DINF in this p-balanced way, and an LLT polynomial that's constructed from the south runs in the lattice path, ordered and so on according to how far they are below that line. And the left-hand side is now another operator in the Schiffman algebra called the Feigen-Symboliak element applied to 1. And this sequence B1 through BL that indexes it, those are the south runs in the highest path that's under that line. And it turns out that in the case where the line runs from Km to Kn, that Feigen-Symboliak element is the operator Ek of minus xmn that appeared in the Kn version of the Shuffle conjecture. But now we can do this for any real number, and this tells us what the left-hand side is. And this is, in all of this, the left-hand sides are something manifestly symmetric in Q and T, whereas the combinatorial right-hand side is quite different. And it's an open problem, really, in any of this to understand the QT symmetry of these combinatorial things in a combinatorial way as something other than just a consequence of these identities. All right, so that's our theorem. Let me just give you some hint about how the proof goes. So the left-hand side, the dB applied to 1, after you apply omega to it, the symmetric function involution that switches the elementary and complete homogeneous symmetric functions, it becomes the polynomial part. And this is essentially the definition of a Feigen-Symboliak element. It becomes the polynomial part of a kind of explicit raising operator series in L variables. And it also happens that the LLT polynomial piece can also be thought of as the polynomial part of an infinite series. So Granovsky and I defined some LLT polynomials, quote, for groups, general reductive groups, and the usual ones would be for GLN. But our LLT polynomials are not polynomials, they're infinite series. And in the GLN case, you get the combinatorial ones by taking the polynomial part of it, right? So GLN characters are symmetric Laurent polynomials, but by taking the polynomial part, we're going to just pick out the ones that are actual polynomials. And it turns out that you can just remove this restriction to the polynomial part and take the whole, so phi of dB here stands for that whole infinite formal power series without taking the polynomial part. And on the right-hand side, we have an infinite sum of these infinite series version of the LLT polynomials. And we actually prove this identity. And you'll notice there's nothing about lattice paths in this identity. It's just a sum over all non-negative integer indices A. But what happens is that this kind of complicated index of the LLT polynomial will be an honest tuple of rows when it's a lattice path, and it'll, if you take the polynomial part, it'll kill all the other terms. And then the A's actually become the number of boxes in each column of between the lattice path and the highest one, so that the sum of the A's becomes the area. You also notice that there's no Q to the div in this really apparent, but that's because the Q power factor by which the L's differ from the G's is kind of miraculously exactly that Q to the div, and it just takes care of itself. So I think I said a little bit on the already about what's on this slide, but what happens is when you take the polynomial part, then this infinite series becomes finite, and the surviving terms correspond to lattice paths under the given line. The sum of the A's becomes the area, and the div appears as the Q power factor relating the L to the polynomial part of the L to the G. And once you have it formulated as an infinite series identity like this, it turns out that more or less, I mean, there are some small tricky details, but it's more or less, in essence, a corollary to a kind of Cauchy formula for non-symmetric Hall-Littlewood polynomials. So what else can we do with this? Well, one thing we can't do is that the KM, KN, and the original Shuffle theorems have a compositional extension. For the original one, it's due to Hagelin, Zabraki, and Morse, and for the KM, KN one, it's in the Bergeron, Garcia, Sergo, Levin, and Jin paper. That we don't have, and it's not even clear what that would mean for paths under an arbitrary line. So we don't know quite what to do there. But we can prove some other conjectures, and we're in the process of kind of madly trying to get this all written up, and hopefully we'll do that within the next, by the end of the summer. We can do the extended delta conjecture of Hagelin, Remmel, Wilson, which is some different, not the nabla, but some different operators from McDonald theory applied to EK. So there's these delta operators. And there's a combinatorial right-hand side conjecture for that, which is also a sum over lattice paths with LLT polynomials. It's the exact same flavor. And we can get an infinite series version of that and do it in much the same way. And we can also finally get the conjecture of Loren-Warrington for nabla applied to a Schur function, which also, again, was a conjecture that this is equal to a combinatorial expression involving now arrangements of nested lattice paths, but again, essentially a sum of LLT polynomials indexed by lattice paths. So that's all I have to say.
Thanks, Mark. That was a really great talk. There are a couple of questions on the chat that I will start with. One of them says that the setup of P be rational makes Theodore, I don't know how to pronounce this name, but he's asking if there is any connection with irrational polytopes, perhaps via Herhart functions.
Not really. The assumption that P is irrational is just, it's kind of a convenience. You could let it be rational, and but then when you define a balanced hook, you have to be a little careful about one of the inequalities should be equality and the other one you know, one should be a weak inequality, one should be a strong. It just is more delicate. But in the definition of balanced hooks, you're always comparing P with rational numbers, the leg over the arm plus 1 or the arm plus 1 over the leg. So it's just easiest to assume, to perturb the line a little bit, assume the slope is irrational and never deal with those ambiguities. But there's nothing really essential about that.
Mm-hmm. And then Per is asking if is there any generalization of the square path theorem?
We kind of haven't looked at that. Probably you could do it like this, but the square path theorem has been sort of Serge-Levin, I think, has kind of a nice reduction of the square path thing to the shuffle conjecture. And so sort of applying these techniques again to try to get that would be, so in a sense, redundant. So we hadn't really made a serious effort to do that.
And again, Per, magical questions. Any new insights on LLT polynomials in general, combinatorial Schur expansion?
I would say yes. In working with these kind of L versions of the LLT polynomials, a lot of nice things happen. So for instance, in these formulas, the index is a tuple of single rows, but in general, you can have LLT polynomials indexed by tuples of skew shapes. And the relationship between the skew shape form and the single row form is basically the skew shape version you can write as an alternating sum of single row ones that looks kind of like the Jacobi-Trudy identity. And if you do that with the G's, there are like mysterious Q powers in there that are hard to handle. But if you do it with the L's, it's completely straightforward. So there are a lot of things that they seem to shed some light on.
Okay, and Francois is asking if there are any analogs of this in trivariate case or multivariate.
So far, this is all very much Q and T. I don't know anything about how this might go to a QTU or more variable situation.
Okay, is there any other question? No? Okay, so let's thanks Mark again.
Thank you.
Very much.